Hi there! I hope that you're all doing very well and are ready for today's class. I, Dr. Rima McMullen, your personal math and physics teacher and a lifelong learner, welcome you to today's lecture. In today's lecture number 7, problem set number 2 of propagation of error, we're going to continue to solve some more problems on propagation of error. This lecture and all of my lectures, they are an effort in the direction of accomplishment of my mission to make education accessible to everybody, to bring education to everybody sitting at their home, to make you all believe that we're all capable of doing subjects like math and physics, that these subjects are not reserved for some elite or specially gifted set of people. We are all capable of doing it, as long as we are willing to put in the time and effort needed to master them. With that being said, in today's class, we are going to solve maybe like 5 problems or so, based on propagation of error, like I said, and you can find a list of all the problems in a PDF document that would be posted in the description for this lecture. And the timestamps for all the problems will be posted as well. So feel free to jump right over to whichever problem interests your fancy. With that being said, let's start today's lecture with problem number 1. Let's see what the problem number 1 says. It says, first thing first, we're going to write down what is given to us. So we are given the length to be 10.00 plus minus 0.01 centimeters. We're asked to determine relative error in the measurement of the length. So what is the formula for relative error? Find relative error in L. Okay, let's come back to this L that is given to us. L is 10.00 plus minus 0.01. This number 0.01, what do we call it? This is called as error or uncertainty. Relative error. What is the formula for relative error? It is defined as the error divided by the measurement. Okay, it may not make sense yet, but it will make sense in a minute, I promise. Let's come back to this L. Let's write this L as L bar plus minus delta L bar. What does this mean? Now, we're measuring length of something. More than likely, we're not going to measure the length just one time. If it's an experiment, in a typical experiment, you will make a measurement several times. And then you will take the average of those measurements. That average is what? L bar here. And likewise, you're going to find the mean absolute error, which is delta L bar. And this mean absolute error, as the name is indicating, it is error. So to find the relative error here, we are writing error at the top over here. So what is error? That is delta L bar. Divided by the measurement. What are we measuring? We are measuring the length, L bar. Okay. Now, whenever we are going to divide this numerically, delta L bar by L bar, we need to make sure one thing, that the units of delta L bar must be the same as the units of L bar. Now, in some problems, these units may not be same. They can definitely give you in some different units, or the error can be given as a percentage. In that case, from that percentage, you need to work backwards to figure out the numerical value of the error. What I mean by that, you're going to see it as we solve more problems. We're going to have examples of most of these things that I'm talking about. For now, let's solve this problem numerically. Relative error is delta L bar over L bar. What is the value of delta L bar? 0.01 centimeters divided by 10.00 centimeters. So now here what happens? Centimeter cancels out centimeters. At the top I have 0.01. At the bottom I have 10.00. So one thing you could do to get rid of the decimal point is that multiplied by 100 divided by 100. Correct? This will make the number at the top 0.01 times 100 to be just 1. And the number at the bottom, which is 10.00, when that multiplies 100, that becomes 1000. I mean, there is more than one way to do it. You're welcome to utilize whichever way you're familiar with or whichever way, makes more sense to you. This is a long way to do things, and if you're taking a test which is timed, multiplying, dividing by 100, writing it explicitly, it's certainly not the way to do it. But for now, like I said, I'm assuming that when I'm teaching these lectures, all the students, they are looking at these things for the first time. Therefore, I am going over these things in detail. I'm showing each step explicitly. But when I solve the same thing, or a similar thing I should say, for a second or a third time, you will notice that I am going to use some shortcuts here and there, but not in the beginning. I hope that makes sense. So here, with that being said, here's our relative error. If you wish, you can write this in decimal form. What would it be? 0.001. Had you been asked to solve for relative percentage error or fractional percentage error, by the way, this relative error, there's another term used for this. It is also called as fractional error. And I'm sure you can see why it is called fractional error, because it is a fraction. Thus, the name is fractional error. Another thing that comes from here is relative percentage error. And it is quite simple actually. It is relative error times 100. Now we already know that relative error is 1 over 1000 times this 100. What does this give you? 1 over 10, which is equal to 0.1%. Here's your answer. The problem didn't ask us to solve for relative percentage error, but we did it anyway. Hey, why not? Alright, so this was your problem number 1. It was more of a warm-up problem. It was a baby problem. Problem after this, the next problem, that will be a level up. Let's call it a toddler problem. Let's move on to it. Problem number 2. It says that a wire has a mass. So let's write down what's given to us. We're given that the wire has a mass m equal to 100.0 plus minus 0.1 grams. It has a diameter 10.00 plus minus 0.05 millimeters. Okay. And the length is 25.0 plus minus 0.5 centimeters. We're asked to calculate the fractional error and the maximum percentage error in the density of the wire. Now, if you think about a wire, when you look at it from a distance, what does it look like? It looks like a straight line. But when you look at the same wire up close, what does it look like? It will look like a cylinder, like shown to you here in the diagram. So this cylinder, this wire, it will have some length L and diameter D, and it will have some mass. Let's call it as M. To get the density of this wire, this cylinder, what do? Density is mass per unit volume. So density is not just of one kind. The density that we're talking about here in this problem, this density is called as volume density. In addition to this, we have surface density and linear density. In surface density, instead of volume at the bottom, you will have area at the bottom. For linear density, instead of volume or area at the bottom, you will have just line, the length at the bottom. You will learn about these different kinds of densities and their examples as the course progresses. Right now, we are going to focus on volume density. Now, we do know that in physics and in mathematics, we like to stick with symbols. We don't want to write this long formula, write down volume, density, spell it out. Instead of this, we're going to write this Greek letter rho. Okay, this is rho. It is typically used for volume density. It has other uses as well. But for volume density, you're going to see rho being used. For surface density, you will see sigma being used. Okay. All right. And we know that mass is M and volume is V. Here we are interested in the volume of what? Volume of the wire, which is going to be volume of the cylinder. What is the volume of the cylinder? It's going to be pi r squared times the length. So in this problem, we're given the value of diameter d, not the value of radius r. So what we'll do is we'll write radius as half of the diameter. M divided by pi times d over 2 square root times L. Okay, this d is supposed to be lowercase d because that's what I chose to write for diameter. Upon simplification, this becomes pi. This equation becomes m times this 2 square, it comes at the top, becomes 4, divided by pi d squared L at the bottom. Now what do we want to figure out? We want to find out the fractional error in the density. So now we know that rho equals 4m divided by pi times d squared L. How do we find the fractional error in rho? We looked at these kinds of problems and the formulae in the previous lectures. So if you have not seen the previous lectures yet, please do so. It will make so much more sense if you have watched previous lectures. So based on that, previous lectures, I'm going to say that the relative error in rho, which is delta rho over rho, equals relative error in m plus, I'm going to take this 2, make this coefficient, times relative error in d, last, plus relative error in length L. Now, why did I not care about the error in 4 and pi? Because these are constants. Constant means that we know it precisely. There's no error in the value of 4 or pi. We know exactly what 4 means and what pi means. Okay. Now it's super easy to solve for this. How? Let's see. Delta M. Delta M is 0.1. Okay. 0.1 grams divided by M. 100.0 grams plus, let's use yellow. Why not? 2 times delta D. Delta D is 0.05. And I believe it's in millimeters. Yes. And D is 10.00. Plus delta L. Delta L is 0.5 centimeters and L was 25.0 centimeters. Now you will see that all of these units, they cancel out very beautifully. Now, next thing is that to solve for this first term, we can multiply divided by a 10. That will give us 1 divided by 1,000 for the first term. But do we really need to do that? I mean, look at the top. There's only one digit after the decimal. And the bottom number, it also has only one digit after the decimal, which it should be if it is written correctly. The error should have the same number of decimal places as the actual measurement. And in this case, these decimal places, they should cancel each other out. I mean, when you divide and multiply by a 10, these decimals cancel out. And the units should always be same. So the units also cancel out. So this gives us 1 divided by 1,000 plus 2 times. Similarly here, when I multiply divide by 100 in the second term. Why? Because there are 2 digits after the decimal. I don't have to write it out. I can just do this much math in my head. I should know this much math by now. And write it as 5 divided by 1,000. Likewise, for the last term, I have 5 divided by 250. After this now, this is simple arithmetic that I'm sure you can all do. So the first one, 1 divided by 1,000 is 0.001 plus 2 times 5 is 10, and 10 divided by 1,000 is 1 over 100. 1 over 100 is 0.01 plus last term 5 over 250. Okay, 5 goes into 250 how many times? 50 times. Now here you don't have to do it, it's up to you. I'm going to multiply divide by 2. It just makes math easier for me, especially if I'm doing it in my head. It becomes 2 divided by 100 now, which is equal to what? 0.02. What does this give me? It makes, okay, delta rho over rho equal to 0.031. Here we have fractional error, also called as relative error in the density of the wire rho. Next, we're asked to solve for what? We're asked to solve for relative percentage error. So this is our relative error, also called as fractional error. And just like in the previous problem, we said that relative percentage error, also called as fractional percentage error, equals relative error times 100. So that gives us 0.031, just picking it up from here, times 100 gives us 3.1%. This is our answer for part B. So quite a straightforward, simple problem. I hope that you found it useful. We're going to now look at another problem of density. Problem number 3. You will see that it is very, very similar to problem number 2. So it is kind of a repetition of problem 2 for your practice. So I highly recommend that you try this problem on your own first and then come back to check your answer. Alright, so I'm hoping that you have tried this problem on your own and now you're back to check your answer. Let's see how I'm going to solve it. Problem says a piece of wire, which is again a cylindrical wire, that is 10.00 plus minus 0.01 centimeter long. So in the given section, I'm given the length of the wire. What is it? 10.00 plus minus 0.01 centimeters. Okay. All right. Now, I did not do it in the last problem, but I'm going to do it here. In terms of just the symbols, I'm going to write L as L bar plus minus delta L bar. Okay. So here, equation 2, it's written in terms of symbols. It's a symbolic equation. While equation number 1, it is written in terms of numeric values. So by comparing 2 and 1, you can very easily see that L bar, which is the average value of the length, it is equal to 10.00 centimeters. And delta L bar, which is the mean absolute error in the length of the wire, it is equal to 0.01 centimeters. Okay. Alright. So this is the length of the wire. Then we are told that the radius of the wire. What is the radius of the wire? 0.200 plus minus 0.02 centimeters. So let's write it down. The radius of the wire. Do you want to write lowercase r here? We can. So lowercase r represents the radius. In the last problem, I used symbol uppercase r. I'm mixing and matching lowercase, uppercase, and the symbols just so you get used to of using different symbols. In physics, you're going to see that there are going to be several symbols on the same page. And you need to get comfortable using those symbols, identifying them. Alright, so radius is equal to 0.200 plus minus 0.00, okay, another 0, 2 centimeters. And just like before, I'm also going to write this in symbols. This gives you that r bar, the average value of the radius, equals 0.200 centimeters, while the mean absolute value of the radius is equal to 0.002 centimeters. Then we have the mass of the wire. Mass is given to be what? Mass of the wire is given to be 8.000 plus minus 0.008 grams, which is going to be equal to what? I'm going to write this as equal to m bar, average value of the mass, plus minus delta m bar, the mean absolute error in the mass. Again, by comparing these two sides of the equation, what do we get? The average value of the mass is equal to 8.000, while delta m bar equals 0.008 grams. What are we asked to solve for? We're asked to solve for maximum error in the density. Okay, so we can solve for delta rho by rho. This is the fractional error in the density. And after you have solved for this fractional error in the density, you can go ahead and solve for delta rho, which is the error in the density. Okay, so how do we do this? To solve this, first we need to look at the formula for the density. It is volume density, mass per unit volume. This is the volume of a cylinder. Volume of a cylinder is pi r squared times the length. And we used lowercase r here. Next, what we're going to do is we're going to now use the formula for propagation of error, which says the relative error in the density, which is delta rho over rho, equals the relative error in the mass here, delta m over m plus. Now if you look at this pi is a constant number. It does not have any error associated with it. It does not have any uncertainty associated with it. So totally disregard this. Moving on to r squared next. It will give you 2 delta r That's a very, very bad looking R. We fixed it. This is the 2 times relative error in the radius plus. Last but not the least, we have this length over here. Relative error in the length. Now we have all the numbers over here. What I have done is I have copied a list of all the variables with their numerical values here in this table over here, just for an easy accessibility. From here we see that delta m bar is equal to 0.008 grams and m bar is equal to 8.000 grams plus 2 times delta r bar 0.002 centimeters divided by r bar 0.200 centimeters plus delta L bar, which is 0.01 centimeter divided by L bar, which is 10.00 centimeters. First thing, you can see that all these units, they cancel out. And when we get rid of the decimal next, we get 8 divided by 8,000 for the first term. This is the relative error in the mass. Next we get 2 times the relative error in the radius, which becomes 2 over 200. And last, the relative error in the length is 1 divided by 1000. Okay, so what does this give us now? 8 divided by 8,000. This is equal to 1 over 1000 plus. Then I will get this 2 goes into 200, 100 times. 2 divided by 100. And lastly, I have 1 divided by 1000. What does this give us? This gives us, the first term is 0.001. The second one is 0.02. And the third one is 0.001. Combine them all and you will get 0.022. This is the relative error. This is the relative error in the density. From here you could very easily get the maximum percentage error in the density of the wire. Maximum percentage error in rho. That is equal to delta rho over rho times 100, which gives you 0.022 times 100 equal to 2.2%. Now, if you wish, you could also solve for delta rho. So we know that delta rho over rho equals 0.022. From here, you will get delta rho equals 0.022 times rho. So what's the value of rho? Rho equals mass divided by the volume. So this mass is the average mass divided by pi average r squared. And once again, lowercase r. Pi times r bar squared times L bar. Let's now plug in the values of the variables. M bar here 8.000 grams divided by pi. R bar 0.200 centimeter square times L bar 10.00 centimeters. Now all I need to do is use this calculator, or if you wish you could, do the calculation by hand. I'm not going to do that. I know how to do it, I'm just not going to do it. This gives me 6.366 grams per cubic centimeters. This is my rho. From here, delta rho will be equal to 0.022 times 6.366 grams per cubic centimeters. Okay. This gives us 0.14 grams per cubic centimeter. This is our delta rho. Okay, so we have solved pretty much everything we could solve for this problem. Problem number 3. We started out with values of the mass, the length, and the radius of a wire, and we know that the wire is in the form of a cylinder. From there, we were asked to compute the maximum error in the calculation of the density of the wire. The first thing that we did, we wrote down the formula for the density of the wire. From there, we applied the rules of propagation of error to determine the relative error in the density of the wire. Once we know the relative error in the density, we could figure out the maximum percentage error in the density by multiplying the relative error in density by 100. We didn't just stop there. We went on to solve for delta rho, which is the error in the calculated value of the density. And here's that. So we have now solved 2 problems where we have applied the rules of propagation of error to the density of a wire. Next, we are going to solve some more problems based on densities of different kinds of things. Let's see what's the next problem. Problem number 4. What does it say? It says that the density of a solid metal sphere is calculated by measuring its mass and its diameter. So we know the formula for the density of any object. It is equal to mass per unit volume. Now in this case, we are talking about the density of a solid metal sphere. What is the volume of a sphere? 4 over 3 pi r cubed. Here r is the radius of the sphere. But in this problem, we're not measuring the radius directly, we're measuring the diameter instead. So what we should do is, we should write this radius in terms of its diameter. So let's say diameter is uppercase D, diameter divided by 2, it is radius. When we cube it, what do we get? M divided by 4 over 3 pi d cubed divided by 8. This 4 goes into 8 2 times. 3 times 2 is the denominator of the denominator. And the denominator of the denominator is the numerator. So this 3 times 2, which is a 6, comes to the numerator. Times this m divided by pi d cubed. This is the formula for the density of a solid sphere. Okay. Next, we're told that the fractional percent error in the measurement of the mass and the diameter of the sphere are 4% and 2% respectively. Let's write that down. We're given that the percent error in the measurement of the mass, delta m over m times 100, is equal to 4%. And the percentage error in the diameter is delta d, okay, uppercase D. It's important to be consistent. Over d times 100 is 2%. Not just that. The maximum percentage error in the density of the sphere is A divided by 1000%. Determine the value of A. Okay, let's go ahead and write down delta rho over rho times 100 is equal to what? A divided by 1000. And we are asked to find A. Solve for A. Okay. So now we know that rho equals 6 over pi m divided by d cubed. We're going to apply the rules of propagation of error to this formula over here. When we do so, what do we get? Delta rho over rho, which is the relative error in the density, equals 6 divided by pi. This is a constant, and constant does not have any error, any uncertainty. So totally disregard it when writing down the uncertainty of the density. This m though, we're going to write down as relative error plus, now comes this 3 as the coefficient times the relative error in d. Okay. We're given the percentage errors in the density, in mass, and diameter. That means we need to multiply this equation by what? 100. When we do so, what we get? Delta rho over rho times 100. It is given to be what? A divided by 1,000. So here's your A divided by 1,000. Next, on the right hand side of the equation, we have delta m over m times 100. It is given to be 4%. Plus, we have this 3 times delta d over d times 100. That is given to be 2%. Okay. A divided by 1,000 equals 4 plus 3 times 2 is 6. 4 plus 6 is 10. That gives us A divided by 1,000 equals 10, which gives you A equals what? Well, multiply both sides of A over 1,000 equals 10 by what? 1,000. That will give you A equal to 10,000. And what are we asked to solve for? The value of A. And we got it right here. So here's the problem, all of it. It looks intimidating, but it really isn't. It's actually a very cute problem. Or at least I thought so. I hope you liked it as well. Let's move to problem number 5 next. Problem number 5. The mass and the edge length measurements of a cube are utilized to calculate the density of the cube. The mass and the edge length of the cube are measured to be 50.00 plus minus 0.05 grams and 20.0 plus minus 0.2 millimeters respectively. So what are we given here? We are given that the mass is equal to 50.00 plus minus 0.05 grams. And as before, I'm going to write this as m bar plus minus delta m bar. And just by simple comparison, you can see that m bar equals 50.00 and delta m bar equals 0.05 grams. What else are we given? We're given that the edge length of the cube, L, is equal to what? 20.0 plus minus 0.2 millimeters. And I'm going to write this equal to L bar plus minus delta L bar. Okay. We're asked to compute the percentage error in the calculation of the density of the cube. So, problem says calculate what? Delta rho over rho times 100. Alright. Now let's see. Solution. The density of the cube is mass per unit volume. And the volume of a cube is m divided by density of the cube. Rho equals mass per unit volume. And the volume of a cube is L cubed, where L is the edge length. Now we are asked to determine the percentage error in rho. Just like in the previous problem, we're going to apply the rules of propagation of error here. That gives us the relative error in rho equals relative error in mass plus this 3 the power of L times the relative error in the length L, which is delta L bar over L bar. Okay. Now we are given these numbers here. So delta N bar is 0.05 grams and M bar is 50.00 grams plus 3 times delta L bar is 0.2 millimeters and M bar is 20.0 millimeter. And just like before, units cancel out. And when I cancel out the decimal, the first term becomes 5 divided by 5,000 and the second term is 3 times 2 divided by 200. Alright, carrying this forward, first term becomes 1 over 1,000 and the second term becomes 3 divided by 100. And this is equal to delta rho over rho. We are interested in the percentage error. So we might as well just go ahead and multiply it by 100. That means each term multiplies 100. What does this give us? This gives us 1 over 10 for the first term and 3 for the second term. So 1 over 10 is equal to 0.1 plus 3. Answer is 3.1%. That was it. That was your whole problem. However, from here, if you wanted, you could have solved for delta rho. How would you do that? Well, you know that delta rho over rho, that is equal to what? From here, 1 divided by 1,000 plus 3 divided by 100. That gives us 0.001 plus 0.03, which becomes equal to 0.031. That is delta rho over rho. You want to solve for delta rho? Alright. Delta rho is 0.031 times a rho. Go ahead and solve for rho. Can you solve for rho? Sure you can. You have the value of mass M and you have the value of the length L. So go ahead and solve for rho. Once you have the value of rho, substitute that in here and you can solve for delta rho. I'll leave this up to you to show what the value of delta rho is. Figure this out on your own. Alright, so this was our problem number 5. Again, simple but an important problem. Problem number 6. Again, this problem is based on applying the rules of propagation of error to the density of a cubic box. Let's see what we're given in the problem. The density of a cube-shaped box is determined by measuring its edge length and mass. The relative errors in the measurement of the edge length and the mass of the cube are 0.015 and 0.20 respectively. What is the relative error in the density of the box? So for this problem, I would highly recommend that you solve this on your own first and then come back here to check your answer. Alrighty, I'm assuming that you have solved this problem on your own first and now you're back to check your answer. So let's see how this is solved and what the answer is. What are we given? Sure, this is a cube-shaped box and the relative error in the measurement of the edge length, delta L over L. If you wish, you can write this as delta L bar over L bar. Okay, is equal to 0.015 and the relative error in the mass is 0.20. Okay, Find relative error in the density of the box. Okay. Solution. Just like we did in the previous problem. The density of a box is rho equals mass per unit volume, and here volume equals L cubed. So from here, delta rho over rho equals delta M over M plus 3 times delta L over L. What are we given? Delta M over M equals 0.20 plus 3 times delta L over L is given to be 0.015. Okay. What does this give us? 0.20 plus 3 times 0.015 is 0.045. Alright, add these up and you get 0.245. Here's the 5 over here, equal to delta rho over rho. Now, if you're interested in finding the percentage error in the measurement or the calculation of the density, what would you do? You will multiply delta rho over rho with 100. That means 0.245 times 100 gives you 24.5% error. Quite a bit of error actually. Alright, so it was a simple, sweet, cute, and a little problem. Not too much to do. As the lectures progress, problems are going to get more and more complicated. But it is like going over one step at a time. Okay? Alright, problem number 7 next. Problem number 5. A scientist measures the radius of a wire using a vernier caliper. It's a tool to measure lengths that are small. Her measurement of the radius in 5 successive measurements are 2.35, 2.38, 2.45, 2.39, and 2.43 millimeters. The percentage error of the radius as measured by the scientist is A divided by 4.80%. What is the value of A? Okay, let's write down what's given to us. We're given the 5 values of radius: R1, R2, R3, R4, and R5. Okay, R5 is 2.43 millimeter. Here R4 is 2.39 millimeter. R3 is 2.45 millimeter. R2 is 2.38 millimeter. And R1 is 2.35 millimeter. Okay. These are our values of the radius, 5 values of the radius. The percentage error of the radius, okay, so the percentage error of the radius is going to be written as delta R bar divided by R bar times 100. This is the formula. What is this given to be equal to? A divided by 4.80. Okay. What are we asked to solve for? We're asked to solve for this A. So that means to solve this problem, we need to solve for delta R bar, which is the mean absolute error in the radius, and R bar. Okay. So delta R bar is given at the top. What is delta R bar equal to? It is going to be the R bar, which is the average value of R minus R1, its absolute error, plus R bar minus R2, its absolute error, plus R bar minus R3, absolute error, plus R bar minus R4, absolute error, plus R bar minus R5 absolute error, and all of this divided by what? We have 1, 2, 3, 4, and 5. This gives us the mean value, right? So this can be written as R bar minus Ri, summation I goes from 1 to 5, and the summation is divided by what? 5. So we see that to solve for delta R bar, we first need to solve for what? R bar. So let's go ahead and solve for R bar. It is going to be R1 plus R2 plus R3 plus R4 plus R5 divided by what? 5. Let's pull this a little lower to line it up with the right hand side. Now I can write this as summation of Ri, where I goes from 1 to 5 divided by 5. Cool? Alright, so now I need to know the value of all of these R's. Alright, R1. What's the value of R1? We wrote it down, it's equal to 2.35 millimeters. R2, 2.38 millimeters. R3, 2.45 millimeters. R4, 2.39 millimeters. R5, 2.43 millimeters. Okay, let's draw a line. This is now divided by 5. What does this give us? All this summation is equal to 12.00 divided by 5. Of course, it's all in millimeters. What does this give us? This gives us 2.40 millimeters. So this is our average value of the R. Next, now we're going to solve for delta R bar. That is going to be equal to R bar minus R1's absolute error. So 2.40 minus 2.35, take its absolute error, plus delta R2 is going to be R bar minus this R2, 2.38, plus 2.40 minus R3, 2.45, plus delta R4 is 2.40 minus R4, 2.39, plus R bar minus R5 gives you delta R5, 2.40 minus 2.43. So the first term here is delta R1, second term is delta R2, third term is delta R3, and so on. And it is implied that these deltas, these are absolute values. What are we doing next? To find this average, that's what the bar implies. We're going to divide this entire sum by what? 5. Why? Because we have here 5 absolute errors that are being added. What does this give us? 2.45 minus 2.35. It's equal to 0.05. This is your delta R1. Delta R2, that is going to be 0.02. Delta R3, now 2.40 minus 2.45, that is equal to negative 0.05. But since we are taking the magnitude only, we're taking the absolute value. That's what these lines here, they imply. It's the modulus. It is going to be a positive number. Delta R4 equals 2.40 minus 2.39, 0.01. And last, 2.40 minus 2.43's absolute value is 0.03. Let's get our line divided by what? 5. Okay. What does this give us now? This gives us, let's see, 0.05 plus 0.05 is 0.10. Then I have 0.02 plus 0.01 is 0.03 plus another 0.03 is 0.06 divided by 5. 0.16 divided by 5. What does this give us? This gives us 0.032 millimeters. Okay. Now what are we actually interested in finding? Our goal was delta R bar divided by R bar times 100 was equal to A over 4.80. And we said solve for what? Solve for A. Delta R bar. Now, in principle, since our R bar is equal to 2.40 millimeters, this delta R bar should round off to 2 decimal places. However, whenever we are doing calculations, we want to keep as many digits as we can for as long as we can. That is until we reach the end. By doing so, we are going to neither underestimate nor overestimate the error. We're going to keep the error more optimum. Okay. So delta R bar is 0.032 divided by R bar 2.40 times 100 equals what? A divided by 4.80. Okay. So 0.032 times 100 is what? 3.2 divided by 2.40 equals A divided by 4.80. We want to solve for A, so go ahead and multiply both sides by 4.80. 2.40 goes into 4.80 2 times, and 2 times 3.2 is 6.4. So your A equals 6.4. This is your answer. So once again, a beautiful problem. Look at it. It is indeed beautiful. I mean, this is what I find beautiful. And I'll probably say this to you every single time. Because every time that I look at it, I fall in love with these things all over again. But that's me. I hope that someday you will get there too, because then you'll find how good it feels. Okay. Alright. So for this lecture, we have solved a total of 7 problems. I hope that you find them useful. I hope that you do try these on your own, because math and physics and science in general is not a spectator sport. You have to get your hands dirty. You have to get in the field. So get the paper and pencil in your hands before you start any of our lectures. And as I work over problems, as I work on problems or theory, whatever it is that I'm doing, you write it down too. You solve it too. You work it out as well. Only then it is that you're going to gain the confidence, to gain the expertise that you would want to gain. Alright, this was it for today. This is it for now. I'll see you again very soon in the next lecture. We're going to go a notch up on the difficulty level on the problems of propagation of error. See you again next time. Until then, have a good one. Keep studying. Keep growing.